Hello everyone, I'm Charmin Khan, and I'm excited to share my project with you. Welcome to my presentation on the 20 newsgroup search engine with advanced ranking methods, and let's dive into my project. So the project is a search engine for 20 newsgroups dataset, which I've enhanced with advanced ranking methods. The 20 newsgroups dataset contains over 18,000 Unisets posts across 20 categories, such as computer graphics and sports hockey, etc. As you can see in this sample of raw data, let's explore why I choose this project. So first, it aligns perfectly with the course focus on network technologies and social interactions by exploring how search engines facilitate information access in networked environments. The 20 news groups dataset shown here in this pie chart of category proportions is a benchmark in information retrieval education, making it an ideal choice for studying search technologies. And this chart shows the distribution of posts across categories, with some like science medicines having more posts than others. So jumping to the objectives are clear. First, I aim to develop a search engine supporting three ranking methods, and I also wanted to index a full dataset with 20 categories, achieve a sub-second search times of less than zero point 0.2 seconds, and provide a user-friendly web interface with features like pagination, category filtering, autocomplete, and query suggestion. So finally, I validate the system's effectiveness through user feedback and performance metrics. So let's see how the system is structured. So here's the high-level architecture of my search engine, broken down into five components: data preparation, pre-processing, indexing, search, and the web interface. It starts with the fetching the data, pre-processing the text to remove noise, indexing the documents using Whoosh, searching with different ranking methods, and finally, presenting the results through a Flask-based web interface. And the diagrams show the flow from raw data to user-facing results. To build this system, I used a variety of technologies. For the back end, I used Python 3.9 as the core language, Whoosh for indexing, and NLTK for the text pre-processing tasks like stemming and stop word removal. For front end, I used Flask as the web framework, CSS for styling, and JavaScript for dynamic features like autocomplete. And here's a screenshot of the initial page load of the web interface, which we'll see in action later. The core of my search engine lies in three ranking methods. So first one, TF-IDF weights terms based on their frequency and rarity across documents. BM25 improves on this by accounting them for term saturation and document length normalization. My custom prosperity method scores documents higher when query terms are closer together, which is great for contextual queries like computer graphics. For example, searching the computer graphics in a computer graphics category might yield different top documents. So TF-IDF prioritize frequency, BF25 balance frequency and length, and my custom proximity favors documents where computer and graphics are closer together, as shown in the comparison table. So one key challenge I faced was incomplete category coverage. Initially, only 11 out of 20 categories were indexed due to a document limit, which reduced search relevance for uh, under-presentationed categories. I solved this by implementing proportional sampling in data preparation step, increasing the coverage from 55% to 100. And these drop-down images show the improvement before only 11 categories were available, and after all, 20 categories are now indexed and accessible for filtering. Now let's take a look at a code that fixed the issue. The snippet from prepare20 newsgroups.python shows the proportional sampling logic, and the prepare data function fetches the datasets, counts document per category, and then samples proportionally to meet the document limit while ensuring all the categories are represented. The highlighted lines I didn't highlight here, but it calculates numbers of documents per category and sample accordingly. This ensures fair representation across all 20 categories. And another important feature I implemented is the query suggestion for misspelling. For example, if a user search neural network, the system suggests neural network using a combination of pi, spell checker, and similarity matching. In the UI, it displays a message that results for neural network search instead of neural network, allowing the users to choose. And the screenshot shows the suggestion in action, improving the user experience by handling common typos. Now let's see the search engine in action. With a live demo, I will showcase several features. First, I will search with computer graphics to compare the three methods, TF-IDF, BM25, and custom proximity. Category filtering for computer graphics, pagination with 10 results per page, autocomplete by typing just COMP, and querying suggestion for neural network, correcting to neural network, and viewing a document like regsporthockey.txt file. But first, I'll walk you through the setup and testing process by running the project's commands in the terminal, explain the code as we go. So let's start with the demo. I've opened a terminal here. I'll run the commands to set up and test the project, explaining each step. Then I will switch to the web interface to show the features. So the first one, I will be running this command. So this installs all the necessary Python packages list in a requirements.txt file, such as whoosh, NLTK flags, and PySpell checker, which are essential for the project. Then I'll run this command, python3 setup.python, which creates a virtual environment to isolate the project's dependencies, ensuring a clean setup. Then I'll activate it with source bin activate, and as you can see in the terminal prompt change, indicating that we're now in the virtual environment. Then we'll be running this command. This script fetches the 20 new scripts dataset using a skip learns fetch 20 new scripts function. It applies the proportional sampling we saw earlier to ensure all 20 categories are represented, and it saves the raw document to the dataset directory. And I'll fast forward it as it's still loading. So you will see a total document copied here, and then we'll run the pre-process. This might take quite a long time, and this script pre-processes the raw documents by removing punctuation, converting into lowercase, removing start word, and applying stemming with NLTK supported stemmer. And the proceeded documents are saved to the dataset proceeded directory, and which will be ready for indexing. And as this may take time, I'll fast forward it again. It's been a long time waiting. We've done generating the dataset and process the dataset. Then next we'll be running the index builder. This script uses whoosh to index the pre-processed documents in the last command, and it creates a Steam mapping to support features like autocomplete and query suggestion, mapping Steam terms like compute to unsteamed forms like computer. This step takes about, I don't know, a minute or 2 minutes for the full datasets, as we'll see in the results. Let me fast forward it again. So it's done in 107 seconds. Then we test the search functionality with this command. So this runs a unit test suite that checks if the search engine returns results for queries like computer graphics, and it validates the TF-IDF, BM25, and the custom proximity methods, ensuring they work as expected. You'll see the text output confirming all test passes. Again, this is taking forever, so I'll be fast forwarding it again. Oh my God. It's done, and it's using around 700 seconds. Now, for this command, it allows me to search the index with from the command line. For example, I'll search computer graphics, and it returns a list of document IDs and scores using the default TF-IDF ranking. This is useful for debugging before launching the web interface. For saving time, I'll be just running the app.python, which allows me to search the index from the starts the fast web server, and I'll open the browser to localhost 5000 to show the interface. So now the survey is running. Let's explore the web interface. First, I will search for computer graphics. So we'll see a computer graphics here, and I'll press search. So, here are the results under TF-IDF, BM25, and custom proximity tabs. Notice how custom proximity prioritize documents where the terms are closer together. And these are the results. And next, I'll filter by computer graphics uh, category to narrow down the results. So, here are the results under TF-IDF. So here are the results. And I can navigate through pages using pagination, showing 10 results per page and a total of 100 results, 300 in total for 3 methods. And let's try autocomplete by only typing COMP. So you see a different kinds of suggestions. Let me type a U, and you'll see a computer here and computers. So this is the auto correction, or I'll just search comp U, and it will still appear some results, and which highlights the computer from different methods. Now I'll search for neural networks. Oh, by the way, here's already the query stuff, because there are results for computer search instead for compute. And if I search for neural networks, the system should suggest neural networks. So displaying the message we saw earlier. Let's see if it works. So yeah, the sentence here, these are the results for neural networks. And so when I click neural networks, it will jump to searching for this term. And finally, I'll click on one of the documents, whatever, and you'll see the full documents here, and you'll be able to view its full content. And that's it for the demo. That's the main functions of my test search engine. So let's jump back to the slides. So let's look at the results. The average search time are quite impressive. TF-IDF at 0.12 seconds, BM25 at 0.14 seconds, and the custom proximity at 0.18 seconds. And all under our target of 0.2 seconds, as shown in this bar chart. Indexing took 25 seconds for, well, actually, it's not 25, it's 107 seconds, as we just experienced it for 18,000 documents, and the memory usage is around 150 megabytes, and which is quite similar to what we saw during the demo. Now, in terms of ranking effectiveness, a user study with 10 participants showed that the custom proximity was preferred for contextual queries like computer graphics, with a 70% preference rate, while TF-IDF and BM25 performed better for single-term queries, as shown in this breakdown. So to conclude, my project delivered a search engine for the 20 newsgroups dataset with 3 ranking methods: TF-IDF, BM25, and custom proximity. Enhanced usability with features like query suggestion and autocomplete, making it a valuable tool for information retrieval education in networked environments. However, there are limitations. It lacks support for advanced query syntax like wildcards or phrase queries, and I'm also trying to run the pre-process and indexing and the searching faster. So I plan to add this support and explore distributed search for scalability later. So that's the end of my presentation. Hope you enjoy and understand what my project is doing. And thank you.